Okay, now let's go back to our elementary topics. You can see immediately that any finite continued fraction is a rational number because those a sub 0, a sub 1, a sub 2, all the way to a sub n are all integers. This is clearly a rational number. Then how about infinite continued fraction? Is it possible for this to be a rational number? Or this might be always irrational? It turns out that if those a sub i's starting from 0 are all positive integers, then this guy must be irrational. And let's read this into a lemma. So, lemma. Let a sub n be positive integers for all n greater or equal to 0. Then the limit in the equation 3.10, let me copy this equation down in here. So this is the equation 3.10. And the lemma says this limit is always irrational. You can't get a rational number when taking this infinite stuff. The proof is not hard. Suppose u, written as a over b, is a rational number. Then, by our inequality in here, this is 3.14 in the book. Then by 3.14, let me copy it here, which says u minus pn divided by qn absolute value is less than or equal to, is less than 1 over qn squared. Now we plug in u equals a over b in here. So the absolute value of a over b minus p sub n over q sub n, which is less than 1 over qn squared. And now we multiply both sides by b times q sub n. And we get a times q sub n minus b times p sub n is bounded by b over. Now you can see the advantage of bounding this error by 1 over qn squared. Because this convergence is so fast, when we take n go to infinity, since q sub n goes to infinity, do you remember why this has to go to infinity? This q sub n goes to infinity because q sub n is bounded below by 2 raised to the power n minus 2 divided by 2, which we proved before. So the right hand side will converge to 0. But if you look at the left hand side, what happens with the left hand side? The key observation about the left hand side is that it is always an integer. This guy is always an integer, and it is bounded by something that will converge to 0. So the smallest non-zero number on the left hand side is always 1. So when n is sufficiently large, the left hand side will be constantly 0. That means a times q sub n minus b times p sub n is 0 for sufficiently large n. And this further tell you that U, which is A over B by our assumption, is equal to P sub n over Q sub n for sufficiently large n. And furthermore, we notice the fact that P and Qn can be chosen to be coprime by lemma 3.1. They are coprime. So, at this point, do you see the contradiction? I'll let you think about it for a while, but I will tell you the answer anyway. So what is the contradiction? The contradiction is that A over B is a fixed ratio. So A, B are both fixed. But this P sub n over Q sub n is changing over the time, and they remain coprime as n goes to infinity. So eventually, this denominator will become larger and larger. When Q sub n becomes very, very large, in particular if it is larger than B, then because Pn over Qn is a reduced fraction with a very, very large denominator, when n goes to infinity, then no matter how you reduce A over B, when you reduce A over B, you can only make A and B smaller and smaller. And if you multiply A and B both by a same factor, then A and B are not coprime, and that makes this fraction even impossible to be equal to this reduced fraction, where P sub n and Q sub n are coprime. So that is a contradiction. It's a contradiction. The key idea here is the coprimeness of Pn and Qn, which is guaranteed by the lemma 3.1. That finishes the proof.